guys, we're going to talk about pyramids. Pyramid is a three-dimensional figure consisting of a base, which is a polygon, kind of like a cone, only not a circle, but a polygon, and three or more lateral faces. The lateral faces are triangles that share a common vertex. See, try to keep it color-coded, red for vertex. Each lateral face has one edge in the common with the base called a base edge. Again, in blue here. See, it's all the way around it. And the intersection of the two lateral faces is called the lateral edge. See, it's in green, color coding. That's pretty good. There you go. So, pause the video if you need to. Okay. All right. Boop. Again, altitude of a pyramid is the perpendicular segment from the vertex to the plane that contains the base. The height of the pyramid is the length of the altitude. Boop. Right there. Okay. Remember, 90 degrees to the base. Boop. A regular polygon is a polygon with all sides congruent and all angles congruent. Okay. Well, I guess you can't see that. Boop. See, all those sides will be congruent. This is a square, so yeah, all these should be 90 degrees. But for the triangle, this is equilateral triangle. Okay, I'll put this in blue. All these sides are congruent. Okay, all these angles are congruent. Do you see the pattern? Do you see the pattern I'm trying to emphasize here? All of these are congruent. Okay, see, that's what they call them, regular polygons. This guy looks a little longer than this one up here. Anyway, but again, angles congruent, etc., etc. Okay, regular polygons. Boop. So we have a regular pyramid. Is a pyramid whose base is a regular polygon and whose lateral faces are congruent isosceles triangles. In a regular pyramid, all of the lateral edges are congruent and the altitude intersects the base at its center. Okay. Again, just for definition's sake, you want to pause the video, write it down, totally up to you. Just emphasizing what a pyramid is. Regular pyramid. Boop. So, the volume of a pyramid is going to be V for volume, obviously, with the height H and the base area, big B, is given by skadoosh. Now, remember, this B is base area. For example, this base is a square / rectangle. Can't really tell, but regardless, that means that area is probably length times width. So length times width will take care of the big B. Okay? So for this example, if we make that substitution, this particular pyramid would have this formula. I don't like that. Let me write this better. We'll have this for the volume. So length times width times height. Okay? Because this substituted for the big B. Now remember, cones was pi r squared because it was a circle, but this isn't a circle anymore. Okay? Hence why for a long time, or really how this is why they introduce the big B, for the sake of it can change depending on the, how can I say, the prism cone of what it is, right? It's a pyramid or a cone. It's still the idea that it's 1/3. Okay? Boop. So, for example, the volume would be 1/3. Ooh, boy. Let me try that again. Would be 1/3 big B times H. So let's research here. The base of this pyramid is a rectangle. So I need to substitute the big B with L times W, H, length times width. Doesn't matter. 2 could be the length. I don't like that. We're going to make it the width. 2 is going to be the width. Again, doesn't matter. 5 can be the length. This 5 could be the height because, altitude intersects 90 degrees. And then you just substitute. So 1/3 Length would be 5 in this instance. 2 for the W width. And height is 5. I think we just do this in our head. 5 times 5 is 25. Times 2 is 50. So 50 over 3. Let's see what that is as a decimal. 50 divided by 3. Hit the SD. 16.6 repeating, but it should be 16.67 inches cubed because it's volume. They weren't specific about decimals, so I just went ahead and went to 2. Okay. Boop. This is fun to do in class about Khufu, but if you wish, you can do it yourself. I'll post the answer. You know, regular shaped pyramid, 756, original height, yada yada yada. Limestone used to construct pyramid. Weighs 160 pounds per pound, cubic foot. Estimate how much the pyramid weighs. So you find your volume, multiply to get the per cubic foot. I had the answer on here. Oh, there it is. So X right here. Yikes. This would squash you. Boop. All right, here comes the real test. This is a hexagon. Okay. This pyramid has a regular hexagonal pyramid. The base has a radius of 2. You know, I'm using this radius loosely, but that means this is 2, which makes this 2. Okay, right here would be 2. Again, I know it looks different because we have it tilted. And the height of the pyramid is 7 meters. Okay, now I'm going to walk this through slowly. You're not going to have a question this hard on the test. This is a hard question. I believe this is doable. This is very doable, and you should be able to do this. This, on the other hand, you'll see is a very difficult problem because it involves breaking this hexagon into 6 triangles, finding the area for one of them, and then multiplying by 6, obviously. Then you have the base area, and then multiplying by the height. So slowly I'm going to walk you through this. As I said, we break that base into 6. Okay, as you know, it's a regular, so this is 60, this is 60, and this is 60. Oh, see, you get the idea, 60, 60 all the way around. But this guy, if we were to split that 60, we get 30. Okay, these are isosceles triangles. So, fun fact, since these are isosceles triangles, that means this should be 60. And this would be 60 over here. 60, 60, 60, 180. They turn into equilateral triangles. So that's pretty neat how that works out. So with that in mind, we can use the 30, 60, 90 stuff we learned back when we were doing Unit 2, the right trig stuff. So flashback, here are those formulas for the 30, 60. You would then plug this stuff in. So our side length is 1. See the 1 right there? And our long leg would be just root 3. Root 3. This gives us our height of this triangle and our base, which is 2, because 1 and 1 is the base, which makes 2. So we would plug that in. Half times 2, root 3. Well, 2 times a half is, well, 1. So now we have root 3. And this 6 comes from the 6 triangles that are around for the hexagon. Okay, this root 3 ultimately serves as the area for one triangle. So now we have 6, so 6 root 3, and that is our base. Now that we have our base, we can plug that in to the formula. So 1/3, now I'm talking about volume, 1/3 times the base we just solved for, times height. Make your substitution, multiply, if I wanted a decimal. So it's 24.25. I would argue this is the hard part, finding the area for a triangle. This happened to be easy because of the hexagon. If it was something else like a pentagon or anything else like that, you would probably have to use trig, or you may or may not get away with this special triangle formulas. Needless to say, you had to find the area for one of the triangles, okay, and then obviously multiply it by how many ever you need. That's the typical setup for these polygons that are greater than 4 sides. Okay? Again, I'm not going to have a test question like that, but you should be able to do a rectangle. And I think that's all I have. Let me check. Again, these should be very doable. All right. I can't find my notes about it. We're supposed to do cross sections, but I can't find it. Anyway, we'll go over it real quick. Let's say we got a couple things we need to discuss. Let's say we had a circle, and if I were to spin it really, sorry, that was my phone. Anyway, if we were to spin this circle around this axis really fast, what shape would we get? That's right, a sphere. I'm just going to bubble that in. That's my sphere. Okay, that's terrible. Let me do better. We would get a sphere. That is even worse. You know what? I'll just get the line tool again. Nope. There we go. You'll get a sphere. Let's see, this will work out. And it does not. Can I click? Oh, yes. Make it bigger. Put it right there. Aha! It would be a sphere, kind of like a basketball. Okay, another one. What if I were to spin? Let's try this. If I were to spin this shape, yeah, you got to really use some imagination. If I were to spin this shape, we would get a cylinder. That's right. Oh, no, boy. Well, you get the idea. Another fun fact is cross sections. Okay. Again, using your imagination, you can practice with IXL. But if you were to slice a sphere, what shape would you get? When I mean the shape, I mean the surface touching that line. You know, and it's really hard to demonstrate. We were going to play with Play-Doh for this lesson, so you could get these cross-sectional shapes in your head. But you're just going to use your imagination. So if you were to cut that sphere, you would have... God, wait. Man, get off of me. There we go. Sheesh. Where were we? You get a cross-sectional sphere. Now, same example here. Let's look at the cylinder. Cylinder, on the other hand, if you were to cut it this way, you would get a circle for the cross-sectional area. If you were to cut it this way, straight down the middle, you would get a rectangle. And really neat is when you cut a diagonal, you would get an oval. Okay? So, that's about all I got for these cross-section. It's easier to, play with the Play-Doh and see them, but we didn't get that opportunity. So, go figure. Anyway, we'll talk to you later.